So, we have talked about work and now we are going to talk about heat. Now, what is heat? Now, people, so you can think of heat as that you have a container, let us say, full of water, and you are using a burner. I am trying to draw a burner, and suddenly you will see that in all sense of hot and cold, the water has become hotter, right. You can touch it, it is like warmer. That is what we do. Now, right now we understand probably what is happening, but people long back thought, and we have shown you also the history of thermodynamics, that Lavoisier thought that there is some kind of a caloric fluid that is going inside from outside, which is there, it is hot, the burner is hot, and that is going inside the water and it is heating it. So, that is understandable that something is going on, but what happens when, let us say, two objects are, let us say, two cars, I cannot draw the car. So, I am just drawing this to squares, are coming with a velocity v. So, it has a kinetic energy of, let us say, half m v square, it has a kinetic energy of half m v square. So, the total kinetic energy is basically m v square, and they collide with each other, and it has 0 velocity, 0 kinetic energy. So, from m v square it goes to 0. So, where does that energy go? People already knew that energy is is conserved, because that means whatever energy is there, it will be conserved, it will be there. So, does it mean that conservation of energy does not hold? Because initially they had velocities, now they do not have velocity. What has happened? Where did that velocity go? So, people realize that when they touch that object, it was hot. Similarly, I told you about that cannon boring experiment also, that with that cannonball, when they tried to make a hole and all, then it became so hot that it could boil the water. That was also kind of a mechanical work, right, that converted to heat. So, there is some relation between these motions, velocities with the heat, that people knew. We will see that we can actually, even before going there, we can qualitatively estimate a certain things. One thing is that, let us say talk about water. We know that if we put some amount of heat, that means if we heat the water for 5 minutes, the water will be the temperature will increase to some amount. Now, let us say we heat the system for 10 minutes, will the temperature be same? No, it will be more if we heat for much longer time. So, these are qualitative observations that people had, and they saw that the heat is proportional to temperature. Now, you instead of, let us say, take one small beaker water and then take a bigger beaker water and again heat them for 5 minutes individually, will the water be, temperature will be increase same? It will not be the same, right. So, because it depends on the amount of water. That is why when you take a big, when people cook, right, they need a lot more time to cook for 10 people than to cook for 2 people, because then it will be quicker. Or you make, this we always see when you make tea, for example. Tea for one people is very quick, but if you make it for 10 people, you need to put in lot of heat, lot of time in order to boil the water. So, which means that the heat is also proportional to mass, right, mass of water, let us say. Now, turns out that these are the two quantities that the heat will depend on, mass of water and the temperature for water. So, given these two things, one can actually see that, okay, by knowing how much water is taken into consideration and how much temperature increase has happened, one can estimate the amount of heat, and that we can call that. So, we can now define a new unit for heat as calorie. So, 1 calorie will be when 1 gram of water is increased by 1 degree centigrade, the temperature is increased by 1 degree centigrade. So, this is by definition we are taking that. So, there is no constant in this. in this particular water. So, whatever the constant, so what kind of constant do you think we will have? Yes, it can be, but you know it is your definition. So, you want to put the definition of calorie, see, because you are starting with the definition. How do you otherwise estimate the amount of heat? So, you take 1 kg of water or 1 gram of water, and you see that the temperature increases from 22 degree to 23 degree. What is the value you are going to ascribe to that heat that you have put in? You say that that is 1 calorie. So, you are defining 1 calorie by the fact that when 1 gram of water increases its temperature by 1 degree. You see, it is your definition, right. So, this is how calorie is defined. I would write here the definition. Now, you write that it looks that okay. So, once we define that, it will not be the same for everything, right. For example, if we take a rod, and in order to extend that rod, or sorry, in order to increase the temperature of that rod by 1 degree, do you think only 1 calorie heat will be required? So, what does, how much, you know, let us say to increase by 1 degree for a rod, particular rod, let us say iron rod, what do you think it will depend on? The amount of heat for a metal rod, what on which kind of quantity the temperature increase will depend on. That means, in order to increase the temperature by 1 degree, what is the property, what is the thing that it will depend on, what is the property of that metal? Let us say we are taking iron rod. So, let us say if I take iron rod and I want to increase by 1 degree. So, will the heat be same all the time, or it will depend on something? Nature of? No, I have told you that it is actually an iron rod. Anything else that you can think of? It is an iron rod, let us say. Now, mass will come into the picture. Now, in the case of iron rod, so let us say if I give you a rod, or let us say cylindrical rod, then in that case mass will be evenly distributed, right. So, and therefore, you can say the length of the rod considered. For example, if you take a 1 meter rod, the amount of heat is required to increase the temperature by 1 degree will not be the same if you take 2 meter rod, because you can think of that as take 2 meter rod, cut into 2 pieces, you get 2 1 meter rod. You give heat and increase 1 degree, you give another some heat and increase 1 degree. When you join them, you would have given the same additional heat, right, which means that it will depend on the length of the rod. So, your in that case of, let us say, when you change a certain length, or let us say increase of length, because we have also seen that temperature, increase of temperature will be proportional to increase of length for a metal thing. So, this will be proportional to length of the rod. Similarly, increase of volume for a gas molecule will be proportional to the volume. So, this turns out that there is some coefficient called coefficients of thermal expansion, which is alpha, that depends on that for a particular metal, which is a metal for a particular material, which is a material property, that it says that how much expansion is there for a given value of the quantity, right. So, in case of other systems not metal or not water, your heat then will depend on mass of the system, temperature, and something called specific heat, that is the property of the material. Because if you take iron rod, then increase in temperature will not be the same if you take copper rod or aluminum rod, right. So, that means the tendency for increasing the temperature or absorbing the heat, because and to increase the temperature, every material will react differently. So, once you know the specific heat of the system, then by measuring the temperature, see, heat measurement, it is not a direct thing, you have to associate that with temperature measurement, and we have already discussed how temperature can be measured, because these are the quantities that we defined. Temperature can be again measured by the thermometers that we have, gas thermometers and many other things. So, essentially we are actually talking about one material property to another material property finally. We have taken the gas thermometer to understand how to define the temperature, and then we are using that temperature to understand how to define the heat qualitatively and also quantitatively, but we do not yet understand the microscopic picture of that. Now, how do you get the specific heat of the system? So, let us take that, let us say that we have taken water system, water in a beaker, and let us say its temperature is T1, and I have a metal rod which temperature is T2. Now, I have to I do not know the specific heat of the metal, okay. Let us say it is C. Now, when I dip into that, then the system will have water in which the metal rod will be there. Final temperature will be somewhere in between. Let us say this T2 was larger than T1. So, final temperature will be somewhat in between. Again, thermal equilibrium will come into the picture, right. When two objects are in contact with each other, there will be thermal equilibrium and temperature will be the same. So, when they are in equilibrium, then the temperature of the metal rod and temperature of the water will be the same. Now, if we assume that the whole process is done in an isolated manner, that means no heat is coming in and out of this particular combined system, then we can say that, and since T1 was higher. So, what will happen is that the water will get heated up and the metal rod will get cooled down, because metal rod had higher temperature by assumption. So, the change in heat for the water will be mass of the water and final temperature minus initial temperature, because specific heat of water, why we do not have C there, because it is taken to be 1, and that is why we can define that calorie as 1 calorie, plus mass of the metal rod, I am taking capital M, then Tf minus T2 and specific heat, and overall it will be 0. Now, since T2 was larger than Tf, this is a negative quantity and this is a positive quantity, right. So, you can balance them and you will be able to find the specific heat of the system, because you know this one, you know this one, you know this one, you know this one, and only thing that you do not know is the C. So, without knowing the specific heat of the system, just because we have defined heat in terms of water, we can now calculate the specific heat of the other system as well. And then once we calculate the specific heat of the other system, then we will know how much heat goes into the system. So, once we know the C, so let us say we will write again C m delta T. Once we calculate for a particular system the C, then later on by measuring the temperature, we will be able to calculate the heat that goes into that particular system, right. So, we are using one standard and then therefore, we are measuring all other things, okay. That is the idea. Now, let us see that we have discussed all that, we have discussed all of these things that are here. Now, the question is that what will be happening in during the phase change of a system. So, when the two systems are in the same phase, that means if I take a system of water at T1 and T2, then we know that Tf will simply be T1 plus T2 by 2, that is not a problem. But let us see if I have ice and we give heat to the system, what is going to happen? So, let us say that this is the temperature of the system and we start with ice. Now, what is the temperature of the ice? What do you think the temperature? 4 degree. What is the ice temperature of the ice? He is right, 0 degree and below, because ice can also stay below 0 degree, right. For example, our freeze has minus 20 degree deep freeze, the ice is there at that, right. So, it can go below 0. So, that means below 0 it remains as ice. For example, water remains within the range of above 0 to 100, is not it. So, similarly it can go below 0. So, let us start with minus 20 degree centigrade of ice and we give heat to the system. So, what is going to happen, because we are giving heat to ice and ice is there in the same phase, means ice phase is remaining till 0 degree. So, the temperature is going to increase linearly, because there also it will be mass into the delta T will be the amount of heat that is going there. But once it hits 0 degree, what is going to happen? Temperature is going to increase anymore? Temperature is going to remain constant. However, you are still giving heat, you are giving heat let us say at a continuous rate del Q by del T, you are giving every 5 minutes some calories of heat, every 1 minute some calories of heat, right. So, your more time is now more heat equivalent to. So, you are constantly heating the system at a given rate, the heat is flowing into the system at a given rate, and what you observe that when it hits 0 degree, the temperature is no longer changing, temperature remains same, but you see that ice is melting. So, what is happening is that that heat is now working against the what ice, now heat is now working against the internal energy of the system, is not it. So, earlier we will talk about that. Earlier it was, what it was doing is that it was changing its kinetic energy, now it is trying to change its potential energy. Okay. However, kinetic energy plus potential energy is the internal energy. So, it is always changing the internal energy anyway, but earlier it was only changing the kinetic energy, all potential energy also, but not that much, because it is still remaining ice, not significantly. But when it melts, starts melting from ice to water, then the potential energy of the system, which comes from the interaction between the particles, that now is going to change, and therefore, ice is now going to melt to water. Now, when all the ice melts, now this one is latent heat, right. So, again it will be, so here it will be mass of ice into delta T of ice. Here the temperature is not going to change, however, heat you are supplying. So, that is the latent heat of the system multiplied by the mass of ice, right, that much heat is going. What is the latent heat of ice? 80 calorie. So, it is, let us say if it is 1 gram, so it will be 80 calorie will go into melting 1 gram of ice at 0 degree centigrade to water. That means, that much energy is now used to break the hydrogen bonds in the ice, and not all of them, right, partially, because water also has hydrogen bond. When all of them melts, then it is again trying to, it is going to increase, and then when it reach 100 degree centigrade, then again latent heat of vaporization will come into the picture, and it will spend more calorie again, and then more than that it will be the superheated steam more than 100 degree, because after vapor it is not going to remain as vapor, right. And more heat you put is going to go into the kinetic energy of the system, because it has already lost all the potential energy that it had. Now, it is just going to go into the kinetic energy of the system. Now, the fact that I am telling you a little bit beforehand will come clear later, that why we are saying that when it goes into the gas system, then only the kinetic energy that is going to change, that will become clear later. So, now, the kind of problems you can try is that, let us say you have a system that water is at 70 degree centigrade and ice at minus 40 degree centigrade, same 1 gram, let us say 1 gram of water and 1 gram of ice. If you mix them together, what will be the temperature? You can try that. It is slightly complicated, because this latent heat is coming into the picture, right. If you have, let us say 1 gram of ice, but if you have, let us say a huge amount of water at 70 degree, then you are sure that final one it will be water only, and then you can calculate all the heat that is required to melt the ice and then increase that and everything, right. But if you do not know what will be the final state, so there are 3 things possible. One is that combined system will become ice, combined system will become water, or it will be an water ice mixture. So, you have to see all possible combinations to ultimately see that what is the final result that you are going to get. Okay. So, this is the most complicated problem that can be possible in these calorimetric problems. Now, we have to understand what is heat. So, we understood what is heat, how that heat is something that increases the temperature, that way we understood what is heat. But microscopically what is heat, or how do we understand when the cars collide, the kinetic energy whatever was there before mv square of the two car suddenly goes to 0 and things getting hotter. Now, where does that go into? So, both the cannon boring experiment and Joule's paddle wheel experiment showed that heat is nothing but energy, or heat is nothing but kinetic energy of the system. How he did that? So, he took let us say a system of water in which there is this kind of paddle is there, like a fin kind of thing which can rotate, like the you remember when when you cook dal and the dal, dal, right, dal does not get boiled properly, then you do that, right. So, that kind of arrangement if it is there along with a pulley, such that when you pull that pulley, that will rotate. So, what will happen? It will churn the water, right. So, that kind of system is attached here along with a pulley, and a mass is at rest at this particular position, let us say. So, now he released the mass and the mass drops by an amount of h. Now, what would happen in that case? If that is the case, then when the mass goes below by h, the kinetic energy should be mgh, right, potential energy gets converted to kinetic energy. Now, that was what expected, that a mass falls by height h, my potential energy of mgh will convert to kinetic energy of mgh, because energy is conserved. What he observed is that the kinetic energy was not mgh, was less than that. Okay. Where did the kinetic energy go? He showed that whatever the kinetic energy, it was less than that, right. So, whatever the loss in kinetic energy that he had, which means Ke minus mgh, has been converted to proportional to the delta T of the water here. So, the loss in kinetic energy has been converted to increase in temperature of the water, meaning increasing heat of the water, because temperature is proportional to heat. So, therefore, it could be established that heat is nothing but kinetic energy or energy of the system, I would say, right, because you cannot really distinguish the kinetic energy and all that. It was having potential energy, right, gravitational potential energy, it dropped down to kinetic energy and then got there, right. We will see later on that we can understand that more by the kinetic energy of the system, the heat. But here we can say that the internal energy of the system, which was there as mgh, has some of that has converted to heating the water, and that is why he wanted to do this Niagara Falls experiment, that the top of the Niagara Fall and water falls by 50 meters and the bottom should have different temperature, because the mass that is falling will produce that energy. Because and indeed, like he did not find much of a difference, but when people other people actually measured it in a cloudy day, they got some difference in the temperature between the top and the bottom of the Niagara Falls. And we all the time will see that this. So, this established the mechanical equivalent of heat. So, that means mechanical energy, whether it is motion of a car or dropping of something, is equivalent to heat. It is like what we perceive as heat and what we perceive as internal energy, that depends on our own measurement. When this paper is there just like this paper right now does not have any heat, right, but it has the potential energy. If we burn it means if you just give one small spark, that is just to initiate, right, after that we are not doing anything, it is giving us heat. Where does it give us? From whatever is stored here. So, it is just the way we actually want to ascribe certain things to materials or properties. So, now it is hidden in this thing. I will just clear the page marking. You see now that now when we do not do any work, so let us say work is not there, then our internal energy is equal to heat, because what happened is that the potential energy got converted to heat, there was no work at that point, right. So, we saw before that delta U was equal to W, now we see that delta U equal to Q. So, when you combine them together, what we get is called first law of thermodynamics, delta U equal to Q plus W. So, if W is 0, then delta U will be equal to Q, if Q is 0, then delta U is equal to W. So, first law of thermodynamics is nothing but conservation of energy, only thing is that it specifies into heat and work, that, and also people talk about chemical work and all that, but that is already hidden in internal energy itself. We can take that as internal energy itself, the chemical work. So, now for an infinitesimal change we can write, so this delta, whenever we write delta U, it indicates that one point to another point, change from one point to another point. Q and W are just amount of work and amount of heat, but when you talk about an infinitesimal change, that means a very small amount, then typically we use this notation d, small d. So, du indicates an infinitesimal change in the internal energy, dq is an infinitesimal change in the heat, and dw is an infinitesimal change in the work. So, we write dq equal to du equal to dq plus dw, and you see now that when work done on the system is positive, then your internal energy is increasing. That is how. So, by convention we have to, when we write the first law this way, we have to take the convention that work done on the system is positive. If you did not, some of the books write in a different way, in that case you have to put a minus sign. In that case we can take work done by the system, okay, but use one convention. So, the first law is a postulate that states that there is a property U that is a function of state variables and can be changed in either two ways, either heat or work. Also it is not dependent on path. So, it is a postulate that we will say that when you talk about two states, it will only depend on the states, whichever way I can come from 1 to 2, it does not matter. So, you saw that in our two calculations that you use two routes or two paths, right, we got two different work, but if you calculate the internal energy, you will find that that is 0. Okay. So, what is the internal energy of the system for an ideal gas? Can you tell me? Internal energy of an ideal gas is 3/2 kBT, and we know that, or no, for 1 mole, or let us say 3/2 RT, 3/2 Na kBT or 3/2 RT. So, 3/2 RT is 3/2 PV, right. So, we started from P0 to V0 to 2P0 and V0, right, correct. So, what was the energy here? 3/2 to P0 V0, so 3 P0 V0, right. What is the energy here? 3 P0 V0. So, internal energy in this process did not change, but we got some work. So, when you write this du equal to dq plus dw, and this was turning out to be 0, which means that our dq is minus of dw. So, whatever we calculated for dw, minus of that actually was produced as heat in that two paths. So, one path we got more work, therefore, it will be less heat that will be generated, another path we got less work, will be more heat that will be generated. More or less I am saying because of the sign. Okay. So, you will see that that has an implications, because we want to minimize the heat producing to the environment to get the maximum work done by the system. Okay. So, first law I already told that, and for a cyclic processes it does not depend on path anymore. So, if you start from here and you do whatever you want to do, you do, it does not depend on path, right. If it reaches finally to the last point, then we denote that as a cyclic integral, it will be always 0. Cyclic integral indicates that we start from somewhere, whatever you do, we come back to the same point. So, it is always 0 by postulate, by definition we do not take u. Because we do not take u to be dependent on path, both dq and dw have to be path dependent, then only they can balance that, because if only one of them is path dependent, other two cannot be path independent. One is path independent, but other two are path dependent, dq and dw, and they balance this thing.